because we started basically diving back through sets and set behaviors, functions, function behaviors, a lot of what we think of as the way we do math can be redefined in those terms. There's a very famous book on set theory that spends a very long time defining all concepts starting from nothing more than the idea of sets. There's an equally valid approach that defines everything in terms of propositional logic. One of the problems with the set theory book is it takes about 72 pages to define one. So this is kind of annoying, which means a lot of what I'm going to do today is pedantic a little, but it's designed to give us a leg up in the long run. It's a binary operation. You've heard this phrase a lot. What's it mean? If I was thinking about binary numbers, yes. But in the same sense that binary does mean only work with 0 and 1, the idea of two things really is a fundamental component here. But this is still an operation. Binary numbers are a set. Operations on binary numbers are binary operations.
In terms of function on and off.
Again, that's the same idea as the binary numbers, the two states, right? In this case, binary operations mean we act on two things. And, or, if then. Back in logic, in discrete, I gave you two propositions, A and B, A or B, and we got out a truth value, right? But if I'm thinking about this from that sort of formalistic perspective, I'm thinking about a function that takes in two things and spits out one. So I need a set, and I take two things from that set, I do something to them, and I get out another element of that set. Formally, I would write, I'm even going to use a weird name for my function, I'm going to call it star, and it goes from the Cartesian product of S with itself to S, instead of calling it F. Right? But that would mean that I would take two things, an ordered pair, and I would do star to it. F of xy. Star of AB. And I get out something. I hate this notation for an operation. Well, what I've written here is usually called prefix notation. Or functional notation. But when you write an operation in arithmetic, you don't write it in front of the stuff. You write it in the middle of the stuff. I want to write, instead of star AB, I want to write A star B. Then it looks like an operation, like adding or subtracting or multiplying. That makes more sense to me. This is called, I hope to no one's surprise, midfix notation. And the graphing calculators use this. But older calculators use prefix notation. I want to add these two numbers. I want to multiply these two numbers. If you've taken databases or computer programming, there's something else called postfix notation, where you give it the two numbers and then say what to do to it. 5, 7, add. That's stack notation, or postfix. In calculators, calculators that use postfix notation are usually called reverse Polish notation, because this was developed by a Polish mathematician. But, as far as I'm concerned, it makes a lot more sense to use the ones we're used to in the middle. So we're going to keep using that setup. But that means that my addition idea in integers, in natural numbers, in real numbers, is a binary operation. You give me two numbers, say add, I give you a third number. Multiplication, same idea, yes? If I pick a different set, I could screw this up really easily. Let's consider subtraction. Subtraction makes perfect sense on the real numbers, yes? I give you two real numbers, you can subtract them. And the result will be another real number, yes? But what's wrong with that? Yeah?
There's an exception to the rule. In that, like, you could subtract, if you subtract 2 from 1, you get a negative number, which isn't in the initial.
That's not well defined. So if I have 1 and 2, and I say take 2 away from 1, I'm not still in the, that's bad. That's not right. So one of the things I need on all possible pairs in my set. You've seen this in other places. Who's in or has taken linear algebra? Yeah, good. Matrices. Let's consider the set of matrices with real entries. If I use this set, can I define the operation of addition on that set? Yes? You're nodding at me, Ben, yes?
Yeah.
There's just one problem. You know how to add matrices. Here's a matrix. Here's a matrix. What happens when you add? You can't do that. You're only allowed to add matrices that are the same size, and this is all matrices of any size. I didn't put that. Aha. I need to be a real pain in the ass and be very precise here. If I want to say we want addition, then I need to say we're working with addition on particular sized matrices. Now, if I specified a size and I said, let's use matrices that are 3 by 3, well, then I could do this perfectly well. I could do it for any particular size. Matrices that are 4 rows and 5 columns would be a perfectly definable set where I could now define addition and it would work. All right. So what I really want to say is that it works in this subset, but it didn't work in the larger subset, larger set. So this is the idea of closure, of being closed and well-defined. Questions? Let me actually make that definition formal. So let's suppose I have a binary operation defined on some set, and I have a subset, H. H is closed under the operation if for all elements in H, star, A star B in this case, is also in H. Now, what we just saw was that addition was perfectly well defined, subtraction was perfectly well defined on the real numbers. Natural numbers are a subset of the real numbers, but subtraction was not closed on the natural numbers because I could take two natural numbers, subtract, and get a negative, not a natural number. Even addition has that same sort of failure. Addition on the real numbers, perfectly well defined. I add any two real numbers, I get another real number. But let's consider that subset R star. This is from Tuesday. What's the star mean?
You want non-zero elements.
Non-zero. Is addition closed in R star? Why not?
Because like if you got -1 and 1, you get 0.
Bingo. Matter of fact, that's true for any number. I can take the number, I can add its opposite and get 0, which is not in R star. So it is absolutely possible to have a nice working operation and say, well, now let's look at it in this set. And the hard part is verifying the condition to be true, not false. If it's false, I just have to find one counterexample. You gave me -1 and 1 and got 0. I'm out. I go back to discrete. Showing something is false means find one counterexample. Showing that the universal is true cannot be done by example. It has to be done by proof. The set E is the set of even integers. You had the following question as an in-class example in discrete. Is this closed under addition? Now, I didn't ask the question that way back in discrete because we didn't talk about closure of operations in discrete in the slightest. But what does it mean to show that E is closed under addition? What do I really want you to prove for me?
That like, every time you add two even integers, you get another even.
And wasn't that one of the very first proofs we did back in chapter 1 in discrete? Show me that if you add two even numbers, the result is even. This should be 5 lines at most. Right. What's the proof here? Talk me through it.
Is it going to be by induction?
Nope, I can do it directly. It's a direct proof. What it requires me to have in the back pocket that I can pull out and go here is the definition of what it means to be even. So let's start with that. Definitions are if and only if statements. What's it mean to be even?
N equals 2k.
Where k is
K's any integer.
another integer. So the definition of being an integer is that you're a multiple of 2. An integer multiple of 2. So now that I have this definition, I should be able to show that when I add two even things, I get another even thing. How do I do that? Enthusiastic drinking. Reese.
You could write like n equals 2l for some other like even number.
Well, wait a second. If I have n here and I have n here, those are going to be the same thing.
Oh, I said n.
Oh, thank you.
So then you have
I should start by saying I'm going to assume that n and m are in my set then.
okay.
So let me preface this with let m and n be in my set. Then I have n equals 2k and m equals 2l. And now?
Then you do 2k plus 2l. N plus n equals 2k plus 2l. Factor out the 2. And then since L and K are both integers, you can just like redefine it as like J is another integer.
Because we already know that when you add integers, you get an integer. It's closed in Z. Well, that means that m plus n is 2j, where j is an integer, and that's the definition of being even. Therefore, m plus n is in my set. Please notice the important thing was going, hey, did I actually get something that obeys the property of being in the set I want it to be in? In linear, we did this with subspaces or vector spaces. So this concept shows up in a lot of different places. Proving it's false only requires me to show one. Is the set of odd integers closed under addition? Why not, Ian?
Because if you add two odd integers, you get an even integer, which isn't in the initial set.
I mean, no.
Because 1 plus, give an example, like 1 plus 1 equals 2.
Bingo, end of story. All you have to do is find one where it's broken, you're out. In a lot of cases, we will redefine our operations, change the way we define things from the standard definitions, or change the sets we're using to be things that are weird. Well, in that case, this sort of behavior becomes a little more tedious. Some of these examples in the textbook are rigged royally. My binary operation says pick whichever one is smaller. Now, I need to double check because I was stupid and didn't write down the set. This is in page 13. These are all based on positive integers. So in Z plus. If I give you two positive integers and ask you which one is smaller, is the result a positive integer? I hope so. You're picking one of the two. I could define an operation that always says, give me the first one. You gave me two things, I picked the first one. I could just as easily define an operation that says, give me the second one. I could even go a little weirder. Let's take that minimum from before and add 3. That works. I'm not sure why you would do such a thing, but all 3 of these are valid, well-defined binary operations that are closed, where Z plus is closed under these operations. You take any two positive integers, take the smaller one and add 3 to it, the result is still a positive integer. I don't know why you would do that. Questions about these operations, because I didn't just pull these out of my ass for no reason. One of these is different than the other two. I want you to take the ordered pair 1, 3. That's A and B, and run them through all 3 of these. You should get 3 numbers. Please tell me what they are.
1 for the first one,
Okay.
and then 1 for the next one, and then 6. The last one, right? Or, I mean, 4.
Right.
Sorry.
So I 1, 1, 4. Great. Take the ordered pair 3, 1. Run them through all 3 of these. It would be. I remember quite thoroughly being upset in Calc 3 and in linear and in physics. Because when I switched the order of things, stuff changed. You multiply matrices in the other order, you might not even get the same result. You might not even be able to do it. When you do the cross product, if you switch the vectors, it turns upside down. That middle operation says, give me the first one. You switch the order, it's not the same one.
Does the same go, sorry, for Cartesian products as well? Like if you were.
Oh, absolutely, yeah.
Okay, I thought so.
If you just have 2 sets.
Right.
People, phone numbers. Phone numbers, people, very different result, yes? A commutative operation is one where if I change the order, it doesn't matter. An associative operation is one where regrouping doesn't matter.
Upside down, hey, that's for all.
Yes, that's for all. Now, in linear algebra, multiplication is associative. If you're multiplying 3 matrices together, it doesn't matter which one you do first, which pair. You do the first and the second, or the second and the third, and then multiply by the remaining one. In either setup, you'll get the same answer. But matrix multiplication is not commutative. In vectors, in physics and Calc 3, that product is both. We already know this one's not commutative. Let's take a look at this one. What do you get?
Just get, oh wait, never mind.
Algebra. Be careful.
Like, would you have to do like the whole operation on just the parentheses and then the whole operation on everything else?
So we're going to start with 2 star 5. What's 2 star 5? So then this 2 star 5 star 5 star 9 becomes 5 star 9, which is great. What is 2 star 5 star 9? Uh-oh. Because 5 star 9 is 5 plus 3, that's 8. So this becomes 2 star 8, which is 5. I wrote a sad face, but I'm really not all that sad about this. I just need to know what sort of properties my operation has so I can write down expressions that make sense and ignore expressions that don't make sense. If I have a non-associative operation like this one, then writing down the following is a problem. Because I don't know which ones to do first. Do you? Oops. This is the problem that you see in all those Facebook memes, where they multiply and divide. And you say, you're supposed to do it from left to right. Says who? You've written something poorly. And now you expect me to argue with you about what the right answer should be? No, be clear, put in your parentheses. And stop expecting everybody else to do it for you. By the way, order of operations working from left to right, we made it up in about the mid-1800s. So that isn't even 200 years old. There are books from Da Vinci's era where they write exactly the same expressions with no parentheses and do them 2 different ways in 2 different pages. We made it up. It isn't an argument worth having. Be clear. Questions? I feel like I'm back at the beginning of the street where I was talking about all this formal logic stuff and everybody's looking at me.
My brain hurts.
Yes. It's weird. But in one sense, this is going to take us much further into thinking about things like vectors and matrices and numbers in a way that we haven't before. And we'll get to answer questions like, why do you do this way?
Compared to our lecture yesterday, analysis, this is great.
Oh yeah, analysis presumes some of this has been exposed to you. And you did see some of this in Calc 1. We just kind of glossed through it very quickly. But analysis is going to do the same sort of thing. It's going to dig through all of those deep little bits. Closure, I think, shows up at the beginning of analysis, sequences, lists of like that. Oh yeah, we're going to see a lot of the same. I will also say that I've never taught the 207 course here, but I taught a similar course, another institution. And when you do the theory side of calculus, you get 2 very different reactions. You get people who really like proving stuff. I think none of you are in that group. And you get people who are like, ugh! Most of you are in that group. So that's why it's kind of weird for all three of us, myself, Dr. Burns, and Dr. Knapp, to all be analysts. We all like that stuff. We're crazy. I will also say that real analysis, the underlayments of calculus on a real variable, is harder than I think Calc 2 or Calc 3 is. Because of that need for proof. Stuff you already know works. It works. Why should I prove it? Because you're taking it on faith that it works? No, because somewhere down the line, you're going to be asked a question like this and asked, do you know if that works or not? And I'm going to make you steal one of the ideas, maybe from sequences, maybe from series, and go, oh, this is how I know that works. I can take the proof I did here and adapt. It turns out really in analysis, there are about 5 main proofs and everything else kind of falls out of, oh, we do it the same way we did that one. So you'll get those. Again, that was a fun course. Okay. Operations are really functions. And so I start thinking back to my algebra class. What did I do with functions? Well, I can do all sorts of things with functions when they have similar domains or similar codomains and ranges and things like that. I could put functions together in lots of different ways. The one that jumps out at me is composition. Now, the difficulty with composition is that that's a univariate function, not a binary operation. It's only taking one thing, right? And so if I start to think about this, then all of a sudden I run into a problem where I'm like, but the binary operation you're taking 2 things, spit out 1. So I have to take 4 things to get 2 things to get 1. So I don't like it. But the only reason I mention compositions here is because there is a proof way back in the algebra textbook that composition is associative. And since associativity is one of these properties I want to look at, and composition is going to come up again and again and again, I want to mention this without proving it. So if I have 3 different functions that go from S to itself, any set, then F composed with G composed with H is the same as F composed with G composed with H. Now the whole reason I'm not proving that is because it's a fairly abstract proof. We just kind of wave our hands at it at the moment. The proof is in the text, but I'm not sure it's worth us going through it this way. I will be using composition as a binary operation later. So knowing now that it's associative will help me. I think this is theorem 13. Yes?
If it wasn't associated, we wouldn't be able to use it like that.
Exactly.
Correctly.
I want well, I could, but then I'd have to use it in a different way, right? I want associative operations.
This makes it a lot nicer for us.
Exactly. And in one sense, there are, okay, hang on a second. What? Sidebar. We're going to decide which rules we really like and want to have. and which rules are less necessary. And one of the ones that is the most fundamental, in my opinion, is associative behavior. There are entire other structures we can build with non-associative behavior. They're, in my opinion, more difficult to find easy use for, whereas associative structures are more useful. I'm biased on that because there are entire algebraists who make their entire field out of non-associative operator theories. I'm not one of them, and all of the work I did is in analysis where I really want things to be associative. We're going to talk about something called a group, one of the fundamental requirements for a group. Sidebar ended. More questions? Again, there are things I want in my set, properties I want my operation to have. So here's another definition. Let's suppose I have a set with a binary operation. And I can find some element, I'll call it E for the moment. And E has this amazing property. When I do E star anything, E star S, or S star E, I get back S. In other words, starring by E doesn't do squat. We call that an identity element. What's the only number you add in real, complex, integers? It's the only number you add that doesn't change stuff. The only number you multiply by that doesn't change stuff. If I look at functions, is there a function that I can add to any other function? Back to Calc 1, look at all the functions you have. Is there a function you can add that doesn't change something? I've got x squared, f of x equals x squared. I want to add some other function and come up with x squared again.
Can you just add it to 0?
Bingo. I can define a function to be 0 everywhere. That's a new function. I'll even call it z of x for 0. Presto. I have a new function that when I add doesn't change things. And it works for everything that I'm adding, right? Again, matrices, matrix multiplication. We even called it that, right? The identity matrix, I. But matrix multiplication was restricted by size, so it had to be a particular size. We had a 2 by 2 identity, a 3 by 3 identity. So we have always a matrix full of zeros, a zero vector. I have a lot of places where I have identities. And I have more than one in a particular set for a particular operation. It says up there, E is an identity element, not the identity element. So could there be more than one?
this is hypothetical, but like if we had a set in S, like, this might be completely wrong, like say we had like max AB and our identity element was smaller than the other one, could that make it so any element smaller than the maximum would be an identity? Because if you take like a smaller number in S, the maximum would be S. If you take another number that's bigger than that one, it's still smaller than S, you can still get S both ways.
Okay, but remember, my operation has to be defined for all ordered pairs, right?
Yeah.
So what's your set? And what you're really trying to define is the smallest thing within that set. And if your operation is maximum, right? Then what if I put in the smallest thing twice? I'm going to give you two negative numbers, right? -7 and -1. Then I get -1. But if I give you -7 and -2, you get -2. Is every smaller number, what if I give you -8 and -7? Oops, I get -7 this time. So I have to figure out which way to find that. I don't know if that max operation has an identity in integers. Notice it's specific to the set. If I gave you the natural numbers, well then 1 being the smallest natural number, or 0, depending on which way you do it, would be my identity, because no matter what you gave up here, you get 1, 1. Can I have more than 1? Let's suppose you're right. Let's suppose I had 2 of them. I don't know what they are, but let's suppose I had 2. If something turns out to be wrong, I've basically done a proof by contradiction, haven't I? I like this idea. Let's see if we can do that. Suppose we have 2, E and E prime. You want to call them E and F? I don't care, it doesn't matter. You call them 2 things, right? Well, I know if you take E and multiply it by anything in the set, you get that thing, right? E is an identity. So by definition, E multiplied by anything gives me the anything. I also know it works in the other order. I also know it works for E prime. Right? So it doesn't matter what thing, if these are both identities. What's that? By definition, right here, E times something is equal to that something. So this needs to be equal to E prime. But by this one, something times E prime has to equal to something, which means this also has to be equal to E. Therefore, E is really the same as E prime, and we don't actually have 2 of them. We just have 1. We just didn't know it was the same thing in 2 different covers. We have just done a proof by contradiction of the following theorem, that any set that does have an identity has at most 1.
Is that most?
At most.
Okay.
Wait a minute. At most 1 means we could have fewer than 1, which means we could have 0. I need you to think about this for a minute. What's a set and an operation where I won't be able to have an identity? It's a set you've seen today in this classroom. Now, real numbers have an identity. We already said, but when you're adding, you add 0. If you're multiplying, you multiply by 1.
Like the example we did with just like the odd numbers.
But the odd numbers weren't closed under the operation we picked. So what operation are we going to use on the odd numbers? Addition meant, but we said that if you added 2 odd numbers, you didn't even get an odd number, you got an even number, so we can't use addition on that set, right?
Yeah.
So I need a set with an operation that works.
Addition with positive integers.
But if I add 2 positive integers, I get another positive integer, but 0 is not positive, is it? So there's nothing you can add in the set of positive integers that leaves an integer alone.
Would be the addition instead of even integers.
But 0 is even, and I can add 0 to any even number and get that even number. Jalen, you're exactly right. If I take positive integers, adding 2 positive integers gives me another positive integer. Addition is defined perfectly well on the positive integers, but there's no identity. Because 0 is not positive. Maybe you're not happy about that. Let's think about even numbers, right? If you multiply 2 even numbers, the result is still even, yes? We proved that one back in the screen as well. But there's no even number you can multiply by that leaves stuff unchanged, is there? 1 isn't even. So it is possible for a set to have no identities. A set and an operation. So positive integers under addition, there's no identity. Because the identity I want is not a member of that set. Even numbers, integers that are multiplied by 2, under multiplication. Because the identity I think I want is 1, but 1's not part of that set.
This work with like whenever we experience 0 2.
If I work with addition, yes. Not if I work with multiplication, right?
Yeah.
So again, it's going to depend on what our operation is and how the set is related. Notice there are still places where the operation is closed. I didn't change associativity. I didn't change commutativity. These are all really nice operations, regular ordinary adding, regular ordinary multiplying. I'm not freaking out and defining something crazy. Which could, but why bother? But the whole point here is that even the idea of restricting or changing or adjusting our set even a little can screw stuff up. Identities are nice. It would be nice if we had one. Again, this is an idea. I would like to make sure that I define an operation and somehow have in there at least the idea of an identity. Something that behaves well within my set. Questions? Promise I'm leading to something good eventually. All right, I keep putting a set with a binary operation. I'm actually going to write that as an ordered pair. So I'm thinking about a particular set with a particular operation. Now let's suppose for a moment that this particular set of operation has an identity. So I'm working where I know I have an E. We'll even call it that. Once I have an identity, I can say this identity is going to play a role between other elements within the set. Then if for x, we can find an element x prime so that x star x prime equals E. And x prime star x equals E. We say that x prime is the inverse of x. Now, I will go out of my way to say we have actually defined two different inverses here. We've defined a right inverse and a left inverse, depending on whether we multiply x prime on the right or the left. Well, star. So I really could define two different inverses depending on the way I do my operation. But I'm hoping that if I have inverses, that I can turn around and say it'll be the same on each side. That's not a guarantee. But if I can find an element that has this property, then I have an inverse. Even when I have identities, I don't always have inverses. Integers. We have an identity in the integers, yes? For adding. 0. Every integer has an opposite, right? Give me an integer that's not 0. 2. Then there's -2, right? But if you give me -7, then there's +7. Every element in the set of integers has another element I can add to it and get 0. Even 0 itself can have 0 added to it. And I get 0 as a result. But in that same set, if I change to multiplying, what's my identity? What's the identity for multiplying?
1.
1. Pick a number that isn't 1. Is there an integer you can multiply 5 by to get 1? Well, obviously then, under the rules for multiplying in integers, I have a problem. So let's go to bigger numbers. What would I need to be able to have a bigger set of numbers? What would I need involved to have an inverse for 5? I need fractions. Let's look at the set of fractions. All possible fractions. A multiply. Multiplicative identity is still 1. Does every element have an inverse? Pick any number, integer or fraction. Can you find an inverse? Sure about that, Reese? Promise I rated this one. You were nodding. So if I pick a fraction, right, a over b, then all I need to do is flip it, right, b over a. So 2 over 5, its inverse is 5 over 2. -17 over 31, I get 31 over -17. What do I do with 0? True. There's nothing you can multiply by 0 that will ever give you 1. So even going all the way to the entire set of fractions, I'm in trouble. But if I go to the set of fractions that excludes 0 under multiplication, that works. Then every element does have an inverse. So I like this idea. I might be able to fudge the set or figure out a fudge for the operation, manipulate it a little bit somehow to get me to the place where I do have inverses. But not always, right? If I think of the integers under multiplication, not 0. So I put the star up there. Star means not 0. Then there are only 2 numbers that have an inverse. What is the identity in the integers for multiplying? 1. If I take 1, I can multiply by 1. I get 1. If I take -1, I multiply by -1 and get 1. So there are some elements that have inverses, but most of them don't.
Does this rule only apply to 1, or could it be like 2 times 2, -2 times -2? Like that's-
Well, but remember, I'm looking for the identity.
Okay.
So I've got to get the identity out. 2 is not my identity, -2, 4, whatever.
Yeah.
I've got to make sure I get, that's why I asked what's the identity first. Now that means that there's a hierarchy here. I can't even think about inverses until I know what the identity is. I have to know what the identity is, and then I can say, all right, for this operation I have an identity, now let me look at inverses. Other questions? Excuse me. When my set is large, I have to use operations that we already kind of know and understand. But if my set is small, I can make an operation up out of whole cloth as long as I tell you how it works. So here is an example of a very small set. S equals A, B, C. And I am going to define an operation star on this set. Now that means I need to know what happens if you take anything in S and start with anything in S, right? How many options are there? Well, there are 3 things in S,
Yeah.
but I'm going to take them 2 at a time, right? I've got to look at the ordered pairs because it's a binary operation requires 2 of them. So I'm going to end up with 9 total options, right? I can do A star A star B, A star C, BA, BB, BC, CA. Let me write down all of those. We've got 9 options. I'll make my life easy. I'm going to define an operation table. And because I like linear algebra so much, I'm going to follow the convention we do there, and I'm going to think row first, then column. So when I do the first row, the row containing A, I'll do A star B, A star C, going across this row. So I decided, and I already wrote this table down earlier, that A star A is B, and A star B is C, and A star C is B. That's how I would read this first row. I can fill out the rest of this table for the moment. A, C, B, C, B, A. I made this up out of whole cloth. Completely invented, pulled out of my head. So, question. Is this operation commutative? Why not, Reese?
Because if you take A star B, you get C, but if you do B star A, you get A.
I can do A star C and get B. I can do C star A and get C. All I need is one. However, to determine whether or not this operation is associative would require me to do 27 different calculations 2 ways.
That sucks.
So I'm not going to bother. I don't know if this is associative. I would have to do A star A star A. And I have to do parentheses both ways and see if I got the same result both times. I sure hope I do. I do A star B, A star A, then with B, A star B, then with A. Do I get the same thing? I don't know. Working from a table to determine associativity is very difficult. Working from a table to determine commutative is as easy as folding the table diagonally. If my table has symmetry across that diagonal, then it's commutative. Now that's the same main diagonal we used in matrices, upper left to lower right. And since your table has to be a square, you have the same number of rows as you do columns, because it's got to be S and S. That's a fairly easy comparison to do, flipping back and forth that way. Questions? I've mentioned it several times in passing. On page 25, at the very end of this section, there's a remark about 2 particular quantities that are required for binary operation, 2 characteristics. I need to have every ordered pair work. Every ordered pair has to produce something, a valid output. And every ordered pair has to produce one and only one output. So in the same way that we defined a set as being well-defined, well, we described a set as being well-defined, I need to describe my operations as being well-defined, and those are the two properties. And if we think about dividing, well then 2 divided by 0 doesn't work. It doesn't assign any image. If we think about dividing and we're in the integers, 0 over 2 works, but 1 over 2 doesn't, because we're not in the integers anymore. So it's a matter of what set as well as what operation. Again, there's a list on page 25 with several examples, and I think it's worth looking at and poking it a little. I think one of the homework questions talks about it, but I really wanted to emphasize that what we're looking for is, does this make sense? And I apologize to you all, because as a math person, my definition of making sense is really screwy. So you all need to adopt that little bit of screwy perspective as well. Thank you all very much. I will see you on Tuesday when your first assignment is due. Section 0. If you've got questions, come bug me in office hours.